Hello and welcome to the fourth of our 8-week webinar series called Advancing in Predictive with Alteryx. Here's, before we get started, some reminder dates of our upcoming webinars. Today we'll be covering k-means, but we also have fuzzy matching, decision tree, crosstab, and transpose and time series coming up. So if you're interested, please go and register for those. A few notes before we get started. Yes, this webinar is being recorded and the link will be available before the end of the week. And we will have a Q&A session at the end, but you are more than welcome to post your questions into the Q&A panel as we go along. There is also a file to be downloaded to kind of walk through today's session, and I'll be sharing this through the Q&A tab as well. And so a few introductions. My name is Rachel Mason, and I'm the marketing specialist here at Technion Data Solutions, and Technion is happy to be hosting this series. So today's webinars will be conducted by Dr. J. Kyle Roberts, who is a data scientist here at Technion Data Solutions. A little bit about Kyle. So he's held professor positions at Southern Methodist University, Baylor College of Medicine, and the University of North Texas. He also co-authored the Y-HAT package in R, and he is an expert in multi-level modeling and co-authored the Handbook of Advanced Multi-Level Analysis. So at this time, I'm going to hand it over to Kyle.
All right, thanks, Rachel. Well, hey, I'm excited to be back with y'all. We're talking about k-means today. And so some of you may have used this before, and it's basically what k-means is a clustering tool. But we need to talk a little bit about clustering before we get into Alteryx and actually doing some pretty cool stuff with this. And we're actually going to, at one point today, we're going to hack Alteryx a little bit. So if you haven't had a chance to do that before, we're going to do a little bit of a hacking there, and we'll show you how to do that and the reasons why. But the idea in clustering is what we want to do is make complicated data a lot more simple. And so let's suppose we have this data set that I have, and this is a publicly available data set, but this is information from loans from Lending Club. And what Lending Club does is they match up people who need loans for a certain amount, or for any amount, but I think it's between $500 and $35,000. They match them up with people who want to lend them the money, and then they get a rating score based on that. You can go in and decide, yeah, I want to loan this person $5,000 at whatever interest rate or whatever. And so there's a whole bunch of information in there. And so the problem is when we're looking at that data, it's just, let's say we had a data set that's, a couple 100,000 rows, and let's say 70 columns. It's just too much to palette. There's too much information. And so we could use something called principal components or factor analysis, or principal access factoring is a bunch of different names for all the same thing, or exploratory factor analysis, to group the columns or group each of the variables in this. And so what we might do is we come in and we run our analysis, and we find out on our analysis that these things like term, interest rate, this grade and subgrade, they all kind of fit together in this first factor that we'll call, I don't know, whatever factor we want to call it. We may call it, I don't know, scoring or something like that. And then these other variables that are represented by these green rectangles here, they might fit into factor 2, meaning they all kind of behave the same. And so what we've done is we've taken 7 variables and kind of consolidated them down to 2 variables. And so that's what principal components does. Now, I'm not going to talk about principal components here today, but that is kind of conceptually what's going on. The reason I bring this up is because sometimes there's a lot of confusion between k-means and something like principal components, because principal components looks at columns in your data set, but k-means, what it does is it actually groups rows. And so it says, given all the information we have about each row, or in this case, each loan or each person in our data set, who tends to be similar to each other, and can we think about those in broader terms so that we're not having to try to palette, let's say 200,000 rows of data. We can actually look at it and go, hey, these 75,000 people, they're all pretty similar. And so we can put them in one group, and then these other 50,000 we can put in another group, and then this other 50,000 we might put them in another group. So what k-means does is when you run the analysis, is it says, okay, for example, these, so what are these 10 people? They all tend to be the same. And so we can think of them in this first cluster that we'll call that cluster 1, or we may have some identifying mark that helps us understand what that cluster is. And then these other people, these other 7, we think of them as, hey, they fit together in cluster 2. So conceptually, that's what k-means is doing. And so I wanted to make sure that we're certain about that, that really kind of conceptually that makes sense. But also in terms of what's going on, we're going to put as much information as we can into our k-means clustering tool so that we know we have a better representation of how we want to cluster our data. So let's take this for example. So let's say we have 100,000 people, and the only piece of data that we have about these people is their gender. Okay, so that's not a lot of information. You know, we may get 2 groups, and then there may be something that, you know, else in there we might have a little bit extra, third or fourth, but they'd be really small as representative to how much actually data we have on all these people. And so if that's the only piece of data we have, we're likely just to come back with a solution that says 2 groups. All right, we're just going to split this as a male, female, based on the amount of data or the type of data that we have coming in. But let's suppose then we also have their ethnicity. We have, you know, what state they're from. We have the, let's say, their monthly income or their yearly income, number of children they have, how many cars they have, how many homes they own, whether or not they rent or buy. So the more information we have, the better we can do at kind of differentiating between these groups. And so in that case, we may come back with a 10 or 15 or 20 group solution. So for our, you know, when you have a few 100,000 rows of data, this is really helpful to you. You start saying, all right, this is what I'm seeing coming out of this k-means, and this is helping me understand these groups instead of trying to palette that much data. Okay, so how does k-means work? So what it first does is it picks k random points as cluster centers. Now this is something you're going to decide ahead of time, but I'm going to show you a little trick that we created at Technion to help figure out how many clusters you will need. Now this first point, pick k random cluster points, and so that's what the k and k-mean stands for, is how many clusters. And it's kind of funny it's the letter k and not the letter c, but okay, that's all right. So we're going to pick k clusters, and we're going to say, all right, given our data, we think there are 5 clusters. Now if you were to start Googling, how do I know how many clusters to retain in k-means, if you Google that, you find that's probably the most oft question that is asked. It's like, how do I know how many clusters I have in k-means? And so it's actually pretty difficult to do. And again, I'm going to show you a macro that we developed at Technion to help you make better decisions around this. And we'll get to that more towards the end of the presentation today. So don't leave early, or if you do, make sure you come back to see that at the end, because I think it'll be a really useful tool to you. But let's say we have our data, and we're going to pick 5 clusters. And so what happens is what the k-means does is kind of randomly assigns 5 cluster centers. And then we assign data points to each cluster based on how close they are to wherever the center is on this. Now, I'm going to get mathematical on you for a little bit. This is, when we do this, we're computing something called a Mahalanobis distance. And that, think about, and if it's in 2-dimensional space, this is easy to think about. It's just an XY coordinate. But once it's 3-dimensional space, then it's kind of an XYZ coordinate. But, you know, as we start adding more variables, that, you know, if we have 10 variables in our model, it's kind of a 10-dimensional distance, if you will. But that Mahalanobis distance that we're computing, that's going to tell us how close it is to these theoretical centers that we're just randomly putting out there. Okay, once we do that, we see, you know, we look and we say, okay, based on our, let's say, 5 cluster centers, we see how far each data point is from each of those cluster centers. And then we say, all right, whichever one you're closest to, that's the cluster that you belong to. And then we go back in and we re-look at those cluster centers, and we go, you know what, if we moved them a little bit, maybe we get a little bit better coverage. So we start out randomly, and then we kind of iterate to, all right, we found a good cluster center for if we're going to have 5 clusters. So we're going to, this steps 3 and 4, we're averaging the points, and then we're reassigning data points on new cluster centers. We're going to do that many, many times in the background until we kind of iterate down to that's our solution. All right, so this is really hard to visualize, but again, with our data, I'm kind of show you how to do this. I'll work at it. It's not easy to visualize, but we'll think about it, see if we can't figure out a way to do it, and I'll see if we can't show you that so it'll make sense more to you as we're working with our data. Okay. So again, as Rachel said, and it should be in the chat, all the data files. I'm actually going to use a pretty famous data file called the cars MT cars data file. And if any of you have played around much with R, you'll know that this data set is used a whole lot when you're trying to do proof of concept stuff in R. But also the thing that I did want to show you is that this at the bottom here, this Technion predictive macros, this link, and I want to take you to this link for one reason, is that we've actually updated this, and we're even in the process of updating it a little bit more. If this takes you to this website, and actually if you're on our technionusa.com website, you can navigate to this by simply going to software platforms and then clicking on Alteryx, and that will take you to the platform, and then you can come down and click on these predictive macros. And that's where this k-means cluster selection tool is. And then also the y-hat regression tool. And I want to show you something on that too, because when we did the linear regression, some people were asking about outlier detection, and we have actually updated this tool to include outlier detection. And so all you have to do is fill out one of these. You'll be able to download both macros. And when you get them, they will actually load. Uh-oh. Me log back in there. Sorry. They will load inside Alteryx, and they will actually create a new tab, and the tab will be called Technion, and then both of the macros will appear in there. And again, too, just by filling out this information here, you'll get a free download link. And then what that installer will do is install this tab up here called Technion, and then there's the k-means cluster select tool and the y-hat regression tool. I'm going to take a little second just to show you why we changed out the y-hat regression tool. And the reasoning is on this is because we made just a couple of changes, and the reason we made these changes is because we've added this browse down here that people were asking for previously. And then as soon as that comes up, I'll show you why we added this. So now we can do outlier detection with the regression tool. And so if you see here, what we've done is we've created a QQ plot of the residuals. And what we're seeing is person number 64, row 64 and row 107 really seem to be outliers. Now we can go back and look at our data set and try to figure out why. Okay, so we included that in there now. And then there's other diagnostic plots here that if you're familiar with these diagnostic plots, we just put those in. But again, this is a good chance to show you, all right, there's the outliers. There's those outliers again right there, 64 and 107. There they are again there, and then there they are again there. So they're not bad outliers, but still, we just wanted to put that in because people were asking for it. So we put that in. Okay, back to k-means. All right, so this cars data set. All right, so now that we're looking at this cars data set, what this has is information on 261 cars and the year they were built and where they were built, you know, if it's a US brand, a European brand, a Japanese brand type of car. And so how many miles per gallon they get, the number of cylinders in the engine, how big the engine is, cubic inches, horsepower, how heavy the car is, that time 0 to 60. And then also the year. So what we're gonna what a lot of people are doing is they're usually using these variables out here to predict miles per gallon. And so this is, again, like I said, this has been a pretty famous data set. So, but what we're gonna do is we're gonna use the k-means tool to see if we can actually say, all right, here are the types of cars that they behave similar. Some of these behave similar, and maybe we can cluster them into chunks of cars, and we can get information about those chunks of cars, okay? So what I'm gonna do is go into this predictive grouping, that tab, and I'm not gonna use our k-means tool yet. I will here in a little bit. But what we're looking for is this k-centroids cluster analysis tool. Okay? So we're going to drag that over and pull it in, and then the solution name, we're going to call this, we'll call this MT cars, because that's the name of the data set. what I want to do is pull all of these variables in. So I'm just going to click on all of them. And the algorithm is going to do is take those 7 variables and try to put them in clusters based on the information that we're grabbing from this. Okay. I'm going to put the number of clusters at, let's do 5 clusters in this case. And then we do want to do k-means, and I'm going to standardize the fields. And the reason why on this is because if you have really different scaling on your variables, then what will happen is some of the variables with the larger scaling will tend to get weighted more. If we standardize the fields, then it weights all of these variables the same. So in general, you want to do that. This starting seed is really no big deal at all. What it is this tool uses a random number generator to start. And so if you want to define what that random number is going to be, then, 10 or whatever, then you can actually set that up in there. Okay. All right. So having done that, we go ahead and add all our browsers here. Okay. So we should be good to go. There's the data. I'm not sure why it's saying no valid metadata is coming out, but I think after we run it, it will. So, all right, so I'm going to do this again. All the variables in there, all 7 variables. We're going to standardize the fields. We're going to do a k-means, not the medians or neural gas. I'm actually not going to talk about either of those today, just because of time. We're doing 5 clusters. I'm going to start to seed it at 10. Okay, so we'll run this analysis. It'll take just a little bit to pull out. Okay, but now we can see. Here's the information. This is basically the output that if we wanted to see it from, just giving us information that will actually appear in here. This is what we're going to use to pass through for doing scoring and things like that. And then here is our output that we want to talk about. Okay, so let's go through the output. Remember, we decided there was 5 clusters. Okay, here's the size of each cluster. So 55, 43, 64, 62, and 32. Okay, and then this is an average distance here. So what this is looking at is it's saying how close are all of the data points around this kind of randomized cluster center. Oh, it's not really randomized, it's iterated cluster center. Okay, so our distance is 1.29. So again, when we are running this, we don't want to see one of these as like 1 and another one is 38. That means it's not functioning very well. Okay, here's an idea of the max distance on each of these. It looks like the 5th cluster is probably defining a little bit better than the other clusters just because the average distance is smaller, the max distance is smaller. So that's a good measure there of telling us how each cluster is functioning. All right, and then this idea of the degree of separation, that means like how far are these on average are the parts away, the data points away from each other, not just away from the center. Okay. All right, and then also too, here's the weighting of each of the variables and how they weight towards each cluster. Again, I don't want to talk about that, but I do want to come down here because I want us to see a little bit of this graph. And I'm showing you this because it is very confusing, and we're going to fix this here in just a few minutes. Okay, so if we're looking at this graph, what it's trying to do is to tell us, like, if we were to plot this on a 2-dimensional plane, that's what these principal components are. If we were to plot this on a 2-dimensional plane, how could we think about all of the groups centering around themselves and overlapping each other? So if you look at all the ones, this is hard to see conceptually, but there's all the ones. We can think of those people there as one cluster. Looks like all the 4s are up here, the 2s are over here, the 5s are here. There's the 3s mostly down here, each of those clusters, okay? All right, so it gives us a little information. All right, now what can you do with this? Not a lot. So I'm sorry, we can't we can't actually do much. We're going to need another tool inside of Alteryx to be able to really do something interesting with this. And so what we're going to do is we're going to actually pull out this appends cluster tool. And the reason we're going to pull this out is because now what we're going to do is take the results from our k-means analysis and then assign a cluster number to everybody from our original CARS data set. So I'm going to grab from this this output anchor into the top of this append cluster tool, and then I'm going to grab from the original data set. And again, too, if you're using like a training data set and then another data set to score afterwards, you might do this. But I generally, most of the time when I'm doing k-means, I run this and then I actually then go back and score the original data set. So we'll put an output tool on this, and then we'll go ahead and click run. And what this is going to do is it's again going to run that same analysis that we just ran, and then it's going to assign a score or a cluster number to each person or each row that's in our data set. So you see this new variable out here that's called cluster that we created, and it tells me, so that first car is in cluster 2, that second car is in cluster 3. Okay, and then now if we wanted to, we could do some fun diagnostic stuff. We could, if we wanted, we could pull down a summarize tool and start to get information about, okay, let's group by cluster, and then let's do a let's average the number of cylinders within each cluster. And so now we can start to look at, okay, is there some sort of profile that's being created for these 5 clusters? And so this will also tell us a little bit of information about what's going on with how well we're doing here. So we actually have some people that didn't get assigned clusters, and then we have, all right, so for this first cluster, they have on average, they have 6 cylinders. Second cluster on average 8, and then the third and the fourth cluster, this is interesting because they both average 4, they're really close to 4, and then the fifth cluster is 8. So what this is telling us is, yeah, our 5 clusters are pretty interesting, but they're not doing an amazing job of differentiating on the number of cylinders. But they may do, what may be interesting is that they give us a really good idea about, we'll add this time, the number of miles per gallon that we're getting. So we'll average the miles per gallon for each of these clusters. And now let's see kind of what happens now. And what we're trying to do is drill down to, why did the cluster select tool say, all right, these cars should be in each cluster, okay? So cluster number 1, 6 cylinders, about 20 miles a gallon. Okay, so what we want to look at is the ones that are close to each other. So here's why cluster 3 and cluster 4, even though they both had 4 cylinders, they're really separated from each other. The cars that are in cluster number 4 with 4 cylinders, there's 2 groups inside that. One gets good gas mileage, one does not. Now, the interesting thing with the 8 cylinders is that both of them don't get very great gas mileage. So we got 14 and 16. So there may be another variable that really tells us a lot of information about what's really different between cluster 2 and cluster 5. Okay, and then finally cluster 1 with 6 cylinders at 20, it's kind of right in the middle. So that's probably a pretty clearly defined cluster there. Now, again, this is, you'll hear a lot of statisticians that they'll say things like, hey, doing statistics is as much art as it is science. And this is kind of where this comes in. When we're trying to define, all right, why did this tool, when we said I want 5 clusters, produce this variable, we start to, again, the summarize tool is going to give us a lot of information about what each of those, why each of those variables were defined, or those clusters were defined the way they were. Okay, now, having said that, again, the question that you're all dying to ask, I know you are, because I'm actually dying to ask it myself, is the question of, Kyle, how do we know how many clusters we should select? Okay, it's a great question. I'm so glad y'all asked it. So I'll tell you what, let me go back to our Technion tool. And what I'm going to do is pull in this k-means cluster select tool. So I'm going to pull this in, and I'll set it here. I'm going to connect it to our original data set. While I'm here, I'm going to go ahead and add all my browses, and then we'll talk about this in just a little bit. All right, so let's set up this tool. And how does this work? I'm going to click all of my variables. So I'm just going to go ahead and say, go ahead and select all. And then I'm going to go to this clustering question. And what this tool is going to do is it's going to run a really pretty complicated simulation. And so I'm going to tell it how big I want the simulation to run. So I'm going to set this to say, all right, hey, clustering tool, start with 3 clusters, and then iterate, let's iterate up to 6 clusters, okay? And then run your simulation and tell me how many clusters I should retain. Okay, so we're going to run this. It's going to take a second to run because, again, it's a pretty big simulation tool that we've created here at Technion. And actually, this one's actually running pretty quick. When you have really big data sets, I mean, this could take up to 20 minutes to run if you have just absolutely gigantic data. But it is a really helpful tool, and I'll show you why here. Okay, so the first is that coming out of here, in this first node is basically a data frame that tells you, that has all of these types. So what we did is we looked at the top 26 metrics. There's really kind of 26 really popular metrics for determining the number of clusters to retain when you're working with a data set. So what we did is we simulated across all of those settings and found, like, the KL clustering algorithm in this case says we think that there's 4 clusters. And then the Hartigan also says 4, the Scott 4, okay, so Marriott 4. And then what we're doing with that, we give the actual estimate there, 2, and so we compute all these for you so that, actually, this is the data set coming through, so that the only reason we did it is so we could produce this. And so we have, I'm going to change it to frequency. We could do percent, but we're doing frequency. So we have this tool that now said, all right, we ran this simulation across 26 metrics. And of the 26 metrics, when we're saying split it somewhere between 3 and 6 clusters, among the 26 metrics, 12 of them said you need 4 clusters. And then 10 of them said you need 3 clusters. Okay. There were a couple that said 0, a couple said 2, one that said 6. Okay, said 6 clusters, and so, but just one of those. So that one is, again, probably these are having a little bit of trouble. But what these tools are intended to do is to give you a whole bunch of information about being able to make a decision on the number of clusters to retain. So in this case, we probably would be okay with going with either 4 clusters or 3 clusters. But do notice that 5 clusters doesn't even appear on here, and that's the one that we ran previously. What the tool also does is it just takes whichever one is the most, and so 4, and it goes ahead and it says, all right, if you're looking for a 4 cluster solution, there's your cluster number, and it appends it to the data set. But here's the other thing I wanted to talk about. This is a really great, you remember I told you I didn't like the graphics from the other one. I really like this graphic that we created for you. And so this gives you a really good way of seeing for the 4 cluster solution, like there's cluster 1, okay, here's cluster 2, here's cluster 4, I'm sorry, here's cluster 1, there's 3, there's 2, and there's 4. And so it gives you a lot of information graphically about how much overlap there are in these. And so if you see the differentiation between cluster 2 and 4 is pretty good. However, there is some overlap there. So there might be some tweaking that we could do with this. Maybe there's some people, but the other thing we added to this is that now it's kind of hard to see, but if you zoomed in, you could see, like, okay, person number 152 doesn't define really well. So there may be, I'm sorry, row number 152. So we could go back and look at that row and get some information. However, when you have 20,000 pieces of data here, this is less interpretable. But again, we just added this color scheme on here to be able to help you when you're doing a k-means analysis to go, okay, if all of my clusters are sitting right on top of each other, I probably made a bad decision. Okay, so that's in this tool also. Okay, I know this is a little bit like drinking from a fire hose, but I want to do one more thing, and I tell you what, I'll create a new workflow for this one, where let me grab that data, because you may be asking yourself the question, Kyle, can I do a k-means cluster for just a single variable? So that's what we're going to do with this data set, is we're going to say, what if we just wanted to cluster around cylinders? I mean, is the k-means tool good enough to recognize, all right, to group all the 8s together, the 4s together, the 5s, the 6s, the 3s. So we actually have a few in here that have 3 cylinders, and so I think that's the GeoMetro, if memory serves me correctly. So here's what I want to do. Let's see if we can hack this. So I'm going to pull in the summarize tool just so we can get an idea of cylinders. We'll do a group by and then a count. Let's see how many of each of those there are. Okay. So coming out of here, it looks like we have 2 cars that have 3 cylinders. I can't think of the other one. I know the Geo Metro used to. 125 that have 4. There are some that have 5. I think that's the Chevy. Oh goodness, I'm trying to remember. The Colorado. I think the Chevy Colorado was one of those that had 5 cylinders. So quite a few that have 6, and then quite a few that have 8. Those are much more common. Okay, so let's suppose we ran a 5 cluster solution just on cylinders. What would happen? So let me show you, because we're about to break this tool, and then we'll talk about how we can actually make it run so it doesn't break. Okay, I'm only going to select cylinders. I'm going to call this solution Kyle. And then I wanted, what did we say, 5? Yeah, because we have 5 different cylinder sizes. So I want to see if the k-means tool is good enough to run and actually do 5 clusters when we have a variable that only has 5 options. Okay, I'm going to click run. And as you can imagine, here's my error term. At least 2 fields must be selected. Okay, so what this tool is telling us is, hey, that won't work. You can't do that because you have to have at least 2 variables. Okay, this is true and it's not true. Here's what we're going to do. We're going to add a variable into our data set. And so we'll pull in a formula tool, and I'm going to add a variable, and we're going to call it constant. And then I'm just going to put a 1 in there. Okay. So we put it as byte, or we can put it as double. Anyway, it's just going to, when we run this, now it's just going to put a column of 1s in our data set. Okay. I tell you what, I'll go ahead and add a browse on there just so you can see it for later. There we go. And then now we're going to run cylinders, and I'm going to click on this constant. Because it's just really just one variable that we're running, I don't need standardized fields. That's not going to matter. But let's run this and let's see how we do. Okay, well, we didn't get our error. We do got some weird stuff, right? We didn't get the error we did before, okay? But it did come up with five clusters. Okay, now that is a weird error, but this actually has to do more with what's going on inside R. You can ignore this, or you could suppress it if you want. But look what it's saying. Okay, so cluster 1 has 76 in it. Cluster 2 has 3. Cluster 3 has 125. Cluster 4 has 2. Cluster 5 has 55. Oh, that looks remarkably similar to 125, 3, 55, 76. That's the same solution. So it is doing this. It's doing a great job when we know we know the clusters, and we want to run this analysis with we want to do k-means on just one variable. Okay, now why do I want to talk about this? And why would you ever use this? Well, you'd never use it in this type of scenario. But let's suppose you have sales data, and let's say you're pulling in an item that your company sells a whole bunch of. Let's say you sell 100,000. You have 100,000 sales of this in a year. Okay. And what you're wanting to do is to be able to say, when we sell it, what are the most common quantities that we sell it in? And, would it make sense for us to be able to come behind and say, all right, this is what we're going to use for volume discount pricing or something like that. So what you can do is actually put in that sales number, the sales dollars or something like that. And you can actually sort your data set and run a clustering algorithm to say, okay, you know what, selling 10 of this unit is really like selling 11, or really like selling 12 or 13. But once we get to 15, that's really kind of like selling 20. And so what the tool will then do is actually split up your data set based on how much sales volume you expect. To go, okay, this is where, if you were maybe wanting to make cut points for thinking about how you're structuring the sales numbers or the cut numbers on this, then you can do a single variable k-means, but you have to hack it, like I said. So you'd have to add this constant in there, and then when you run it, you're still going to get the error message, but you're getting the output that you want. Okay, So you are getting those cluster numbers and who's in each one, and so we can actually do something with that. Okay, all right. This may be the most drinking from a fire hose presentation you've ever had. This was a whole lot of information about k-means and kind of how it works. But I did want to show you this, and I think too, kind of where we are with time right now, it would probably make sense for me to turn it back over to Rachel, and then we'll pull up some of the questions that have been asked. So Rachel, if you're on, if you want to go ahead and ask or pull up any of those questions, I'll try to address as many as we have time for. Okay.
Sure. So our first question is, what does starting seeds mean in the tool?
Great. Okay, so good question. So the way the k-means works is it's an iterative algorithm. And so it's in order to start an iteration, we have to have some random number in there where we start doing this. And so this is like too, if you're wanting to do simulation work inside of R, and you and I are both simulating, let's say, a population of scores, and I want you to have the exact same simulation that I do. Because we're able to set a start seed number, and so I say, hey, my start seed number is 1, 2, 3, 4, 6, or something like that. Well, when you run your simulation on your computer, if you don't use that same start seed number, we won't get exactly the same solution. And so there are some times that when you start with random numbers and k-means, and if you change that start seed, you may have instances where some people may move just a little bit. So for example, when we were talking about this graph, and so for this time, because our start seed was what, 10, I think it was, person number one, or row 152 was actually in cluster 4. But if we ran it again with a different start seed number, the people that are out on the fringe, they may move a little bit, depending on which cluster we're going to put them in. These, in this case, these cars, they may move a little bit depending on that. So what you typically, the reason that start seed is there is if you and I are both working in different areas and we want to make sure we're getting exactly the same solution, we need to make sure our start seeds are the same number. And it doesn't matter what the number is, it just needs to be the same across both of our instances. So that's why they put it in there, because if they let that be random, then every time you ran this, the solution might be just a little bit different. And so what they want is consistency across running those solutions. And so that's what start seed means. And that's why they Alteryx smartly left that in there as something that you should keep. Okay. So great question. All right.
Awesome. Okay, so the next one is, I'm not clear why 0 and 2 clusters would be options when the tool is set between 3 and 6 clusters.
So this is a byproduct of, that's a great question. So if we're looking at this, we said we want to go between 3 and 6 clusters, and 0 and 2 appear on there. Okay. Some of these, so part of the problem is that some of these clustering algorithms, these tools that we're using, or the algorithms to determine the number, so we can actually pull these out. So this one here, Dindex, the reason that comes out is 0 is there wasn't enough. The Dindex and the Hubert, they require massive amounts of data in order to actually come up with a solution. And so the problem is that both of those didn't have enough data to come up with their own solution, and so they default to 0. And the same is true with the McLean here. It required, so it didn't actually come to an estimate, and so the default on that was 2. And so that's why both of those appeared. So that's a great question to ask, is why did some of those? So we would want to go back and look at this and see that, hey, there was actually no estimate there because the data set wasn't big enough. There's only 280 rows or something like that. And so because it's not big enough, those couldn't come to a solution. So great question.
Awesome. Okay. Do you recommend to use k-means tool to cluster by multiple fields, or would it be okay to use multiple k-means tools by each field to know each cluster group, i.e. select duplicated fields so that you can select 2 fields for k-centroid cluster analysis?
Um, I'm not sure I understand that. If the thought is that you wanted to daisy chain these, and so I know some people do that, where they'll run an analysis, and then based on that they'll run another one, and so they'll just keep pulling, those tools in. I don't like that, and so generally statistically you want everything running inside a single instance. You wouldn't want to do multiple instances. And again, sometimes people do this also with time series, and I'll talk about that when we get to that one, that they'll daisy chain time series. The problem is you're not running your analysis on your original data. Now you're running it on something we call residuals. And that's always a really, really bad practice. We don't like to do that. And so I think if I understand your question correctly, then that's what you're asking. And so, but yeah, I do want to run it on all of the fields that I want considered in order to run my clustering algorithm. I want in a single instance. So I want them all inside here. I don't want to run some of them here and then some of them somewhere else and kind of try to put those together. I wouldn't want to do that. So, okay.
Okay. Would you use the one variable method to set historical benchmarks or sales quotas for your quantity example?
Yes, that's a great question. Yes, I love doing this. And so going in and when you're using the one variable method, the historical benchmarks is great, or you're wanting to try to say, like you're wanting to go back to your team and say, hey, here are or maybe you're wanting to reward the people that are your sales associates and say, okay, here are the benchmarks you have to hit. And, at this one, you get this bonus. And at this one, you get this bonus. This will kind of help you see what are the natural groupings for those, kind of where your natural cut points for. You would say, okay, if you're coming back and saying, look, we want 3 bonus tiers, then that's exactly what I would do. That's a great, and typically though in that case, what I would do is I'd figure out what the k-means tool said and then add a little bit to it. Because I mean, remember too that k-means is going to be somewhat of an average of those. So if it's if the average is 10, I might put it at 12 if you're looking at it for a benchmark. But that's a great question and a great application. Yeah, great.
Awesome. Okay. How should we decide the best number of clusters?
That's a great question. You use this tool. So again, use this k-means tool for us. And then once that result comes out, again, you're wanting to see, go to this graph. There's how you pick out the best number of clusters. Okay, this is a statistical way to do this. This is purely stats. This is not. This is an objective measure, but again, too, k-means. You'll see. In fact, there's a really good article, and I think the article is titled "K-means is as much science or as much art as science." And I think that was a really good. I can't remember who wrote it, but I remember reading it a long time ago. And it's a really good article because they do talk about, look, if ever there were a statistical method that you needed to apply uh, subjective understanding, this is the tool. So yeah, you want all the stat stuff, and this gives you a good starting point. But it may be that you go, hey, 3 is actually a better solution for me practically or pragmatically. And so I'm going to do 3 instead of 4, but they're pretty close to each other. Three is easier for my company to palette. Okay, great question.
Okay, instead of a constant of 1, what if I just duplicated the single variable I want to cluster on? Is this a valid option?
Good. I don't think it will run if you do that. I'm trying to think of if it will. So I'll tell you what. We'll give it a shot here real quick. So we'll add. So what we're wanting to cluster on. So we'll do cylinder. Well, no, actually, we'll add a column. We'll call it cylinder 2, and this equals cylinders. Okay. And I don't remember if I put that as a double before, but we'll put it as a double this time. Okay, so we'll take that out. We'll run this real quick and let's see what happens. I'm trying to think of mathematically what this would do for just repeating the same. It's not contributing any variance to the model, but it works. Okay, that's interesting. Yeah, that'll work too. Okay. Um, I do need to think. No, that's a great question. I've never been asked that question. Um, okay, that's from Jeffrey Royce. You win the hard question of the day award. Um, so you can do it, most certainly. I need to think though, and we are getting the right solution there. I need to think about mathematically. Is there an issue there that we wouldn't have if we just did putting a constant in? Okay, I can't answer that today, but that's an excellent question. If there were a prize to win out, give out, then Jeffrey Royce, you just won the prize. That's a really good question. Okay, maybe we have time for one more. Is that okay, Rachel?
Yeah.
Okay.
So our last question is, does the k-means tool use a scree plot to pre-identify the number of clusters?
No, so you can use, there is a method for determining the number of clusters. It's called the elbow method that uses a scree plot in order to determine the number of clusters. And so you can, the issue is that you can't inside of Alteryx actually get a scree plot. And so it's not something you can see. So Alteryx is always making you define how many clusters you want. And so the good thing is if you are using our hold on, let's get over to that side of it. If you are using our tool, oh, I'm sorry, I'm on the wrong one. Then I'm trying to remember, there are a couple of these that actually are a derivation of the elbow method within a scree plot, but I cannot on the top of my head, I can't remember which ones they are. I want to say it's the CCC one and one other, but I'm not absolutely positive about that. But yeah, so that's, you can actually, you can plot the eigenvalues on this on a scree plot, and then it's where your eigenvalues are going to kind of make a curve, and then you see where the elbow exists, and then that's what you, those are where you say that the number of clusters are. That's a really good question, really smart question too. But yes, that is one way to actually do this. But and if I can't off the top of my head remember which of these mathematical formulas actually use the scree plot in order to predetermine the number of clusters. That's a good question, though. Really good question. Okay, well, thank y'all very much, Rachel. I'm going to turn it back over to you. And again, I appreciate y'all taking time to meet with us today. That was hopefully a lot of fun, and hopefully you learned something too. And it wasn't too much on drinking from a fire hose there. So, yeah.
Well, awesome. Thanks, Kyle. A few notes. Next week, next Thursday, Dina Sanchez will be continuing our series covering the fuzzy matching tool in Alteryx. So be sure to register for that next week. And today's webinar was recorded. That recording will be sent out before the end of the week. So yeah, I think that covers everything. Kyle, if you want to show them where the predictive macros are one more time, just so that they know where they can find
Absolutely. So again, if you're on our web page, so I'm just going to take to the home screen on our web page. If you're there, when you click on this menu and you go down to software platforms and then Alteryx, as you're looking at everything that the information we have about Alteryx, down here there's this tools and macros, and if you click on the predictive macros, this is where you can sign up. And again, filling out either of these will give you the link for both the k-means macro and the linear regression, the y-hat macro that we have. You can fill out either one of them, it doesn't matter. And then it gives you an installer that all you need to do is run inside of Alteryx, and that will give you this install that actually puts a tab near the end back here that's called Technion, and then you can see there's the k-means, there's the y-hat, and this is the new y-hat that has the outlier detector in it, and then the model diagnostics there at the end. Okay.
Great. And these are free tools that are available for anyone. Well, I think that covers everything today. Thank you so much for tuning in, and we hope to see you next Thursday.